Hi, welcome back to this old hardness tester. As you can see, I finally got a hardness tester that I talked in my last shop talk, shop tour. Finally up on a table, cleaned it up and did some maintenance on it because there were a few things to be dealt with, but did that. First, I built a table out of 45mm aluminum extrusion. I have a little bit of a construction here that I will show. So, cutting the aluminum extrusion to length, I'm using a woodworking miter saw and a lubrication stick, which is basically almost like a piece of beeswax that you push against the saw blade. This helps lubricating the cut and prevents a built-up edge on the saw blade. But in general, cutting aluminum with a carbide-tipped woodworking blade is no problem at all. It works very well and the cut comes out almost like a milled finish. The miniature forklift is good support for the miter saw to get it to a decent height. When you assemble aluminum extrusion, always deburr the edges, otherwise you will end up with a lot of spots on your finished product that you can cut yourself. Also take care of the corners. A wire brush finishes off and removes any remaining fine burrs. Tapping the central hole with the tiny cordless drill. This threaded hole is for the feet that the table will sit on. My preferred way of assembling aluminum extrusion are those die-cast brackets. It's a very fast way. You don't have to drill or mill into the profiles themselves. And they're just fast and very convenient if you have to reconfigure your product that you're building. They are not the most rigid way of assembling. There are larger die-cast angle brackets that are twice the leg length, but in this case the 45mm angle brackets were good enough. The miniature forklift is also for assembly a very nice table because it's height adjustable. Mounting the lower bracing, and you can also see the feet already in place. This is a close-up of how the T-screws and nuts work in conjunction with the die-cast brackets. The hammerhead of the screws drops through the slot in the bracket and twists in place in the extrusion. The top of the table consists of this is 3-layer plywood and cut to size, and I doubled up the thickness using glue and screws just to give the table a little bit more meat. A single plate would have been enough, but I didn't like the look of it, so I took two pieces, glued them on top of each other, and after the glue up I ran the track saw around the edges to clean up any misalignment between the two pieces of wood. And here you see me cutting into a screw that's in the sacrificial board of my on my two sawhorses. Oops. Also, when doing a cut like this, the dust extraction on a track saw does not work. Then I had to take apart some of the mechanics in the back here. I have a little bit of a clip that shows how the mechanics operate in there. This is the mechanism from the hardness tester that selects the stack of weights that's needed for a certain test. And all this mechanism here is you have these fingers which are on these two pivots vertically here, and you have this closing bar back here that's spring loaded like this. And it works like this. Normally you have this plate in front here with those plungers, and those plungers just press against those fingers and select the height of weight, the stack of weights that's needed for the test. And when you want another stack, you just press another button. It works like this, or this. It's not foolproof. You can, for example, press in 2 at once, but that's a case of the problem is in front of the keyboard, not a fault of the machine. And when I got the machine, this lock bar back here, the spring-loaded lock bar, was frozen up. It was completely gunked up on the pivots up here. There are dowel pins running in these cast top plates, and there was just gunk in it. And I took it apart, I cleaned everything, and I put it back together. So it's nice and smooth moving again. Here is the weight stack. You have the retaining plate, and then you have the individual weights that need to go back in the machine in this order, just upside down because I pulled them out like this. And this is the retaining plate for the bottom. And now we need to get the casting or the selector frame back in here, bolted in place, get the weights back in and reconnect the linkage. So this goes in here. And of course it's wider than the cutout in the casting, but fortunately we can engage all those fingers. So now all of the fingers are depressed. And we can drop this back in, lift it up. Okay. There we go. Since I had all of the fingers engaged, it takes a little bit of force on the lock bar to get it disengaged again. So now we drop the bottom retainer plate back in and we engage the lowest lock fingers, and then we just stack the weights in. And it might be a good idea to clean them so they do not stick together. I'm not entirely sure if this can happen, but better be safe than sorry. And we don't abrasive clean these weights. They have a fairly precise weight. This one is only aluminum, so it's super light. All the other ones are steel, as far as I can tell. And right now we're building the lightest possible stack, because basically the whole stack is disconnected from the rest of the machine. And they're nice and tapered on the underside, so they stack very, very neat. So this is the heaviest weight. Alrighty, there we go. That's the complete stack of weights back in the machine. Ow. Okay. Got the pull rod back through there. I'm polishing the plungers that select the weight stack with some 30 micron polishing compound in the lathe, just on a piece of kitchen paper, and a few seconds are enough to clean up any discoloration, oxidation and slight rust on these parts. And it's time to reassemble the weight stack selector. It's just bolted in place with 4 socket head cap screws. Alignment is not critical here. And here you see the mechanism back in operation. So it's time to move the hardness tester in place. It's about 180 kilograms, so the miniature forklift once again helped a lot. And here it's in its final place. That's the final result. One beautiful hardness tester that I horse traded against a construction compactor. This is a Wolpert Testor, with all paperwork. Since the machine has bought, it had 2 owners, of which one is the company that bought it originally, and the second owner is my friend. So I'm the 3rd owner. What is it? It's a hardness tester. It can do hardness. In its current configuration, it's primarily a Rockwell hardness test. It does test the hardness in Rockwell C. There are different classes of Rockwell testing for hardness, and Rockwell is primarily used for through-hardened pieces. You don't use it on soft metals, you don't use it on soft steel. Rockwell C starts at around 33 points Rockwell C to make sense. Below that it's basically soft cheese. You cannot use it on very thin pieces. Then you would use either Vickers hardness or Brinell hardness. Then there is Rockwell B, which uses a ball, but I don't have the proper diamond for it. I have only the diamond for Rockwell C and a Vickers diamond, which is a pyramid shape. On Rockwell C, we have a dial indicator here that directly reads the hardness. You put your piece in here, you do your preloading, you select the right loading, and this indicator, which is basically a 2 micron per division indicator, shows the hardness in a direct reading. I'll show it to you. We'll do some hardness testing today. On Vickers, we have to use a microscope to measure the size of the indentation and then calculate in relationship to the force that we use. The drawback is it's more work. There are testing machines that have an optic integrated. You do your testing and then the diamond swivels to the side and the optic, a small optical comparator, moves in and you can measure the size of your indentations right in the hardness tester. This one, but I have a toolmaker's microscope, so I can do my Vickers testing. So we have the googly-eyed hardness tester here. We have a large hand wheel here, which moves the table for our sample up and down. And we have a table that we can take out. This is the small sample table. This needs to be in very good condition. And I have this large sample table that definitely has never been used. So this screws on here all the way. Very long thread. So it screws on all the way. And then you have a large sample table, which I prefer not to use because for my parts the small sample table is usually good enough. But if I have the need for a large sample table, I have it. So let's so this goes off. And the small sample table drops back in. And then we can move the bellow back up. Whoop, like this. Up here we have a sleeve that screws on and off. And behind this we have the diamond. We are very careful with the diamond because those are expensive. There's a little set screw, and in addition it's held in with a magnet. This surface here and this face here need to be absolutely clean. There cannot be any dust, dirt, burrs or oil. Even oil will make a problem. Otherwise the measurement will not be good, because the tip can rock or settle under load or anything else weird can happen. You'll just get an unreliable result. In my experience so far, which is about an hour on this machine, I just drop the diamond in up against the magnet so it holds it, and then I tighten the set screw just with my fingers, just so it's very secure in there. As you can see, this is moving, and the weight stack in back of the machine that you saw me earlier fixing will press this diamond down. And we have to screw on the sleeve. This has two purposes. Well, it has one purpose and one benefit. For one, so that's normal use with the diamond down here exposed. The side benefit is you screw it down a little bit and your diamond is not exposed anymore. So it's protected, cannot fall out, and it's very safe. The diamond is multi-hundred euros a piece, so we better be careful with it. And the second use is, once you have your part here and preloaded with the diamond, you can very, very carefully settle this down onto the surface of the part to even more stabilize the measurement. We have the weight selector back here, which reads in kilogram, which is not a force but a mass. But yeah, we have 150 kilograms of force on the diamond. That's for Rockwell C. We have 178.5 and 250 is the maximum. And the lowest weight we can do is 15.625, which is probably for Vickers or Brunel. But we're Rockwell C, so we'll stay here. Select this weight, and we have a second control. We have this lever down here, which can be disengaged like this, and then very slowly moves upwards. And the same way this moves up, the diamond moves down. The speed is regulated by an oil dampening system in the side of the machine. There is a little hydraulic cylinder with a valve, and this reduces the speed of the stack of weights falling down. With the lever down, you lift the stack back up and are ready to test again. I have a high-speed steel blank here, which is, as we know, rather hard. I have my precision ground flat stones here. We stone the back a little bit, just to make sure there are no high spots. And we stone the table very lightly, just to make sure there is no dings, dents or bumps in it. And we get our part on here. We expose the diamond, it is. We raise the table with the workpiece into the diamond. Now is the right time to find a good spot for hardness testing. I did some hardness testing on this blank before, so we have to find a spot that's clean. And then we drop the diamond onto it and crank the diamond into it. And how far do we crank it in? We crank it in until the large needle stops moving. That's about when the small needle points at the red dot here. I crank it up, 1, 2, it's usually 2.5 turns. A little bit over cranking, and now we're ready to test. What we just did is preloading it. And then we just take our lever, depress it a little bit, get it over, and let it go. We don't slam it over because it can reset the whole mess. And then we see that the needle moved away. Now we have the needle moved now to some point. And now we go back to the lever and depress the lever and relatch it. We press it down, move it over. So this came out at about 69 Rockwell C. The black numbers out here are the hardness in Rockwell C, direct reading, and 69 sounds about right for a high-speed steel blank. On a good day, this should repeat quite well. So let's do another one. Problem is when it does not repeat, then there is something weird. Then usually your part is not resting very nicely on the table, or you have dirt somewhere. But this is pretty much 69 again, a little bit, maybe half a point Rockwell C under 69. So pretty decent repeatability. And you saw me turning the sleeve down a little bit so it presses onto the workpiece. This stabilizes everything a little bit more. At least that's what's stated in the manual of the machine. So that's the general use of a Wolpert Hardness C tester. There is not too much to it. The problem or the difficulty with it is, as this is reading 2 microns per line, a single piece of dust on here will already alter your results. Or you have hardened parts with scaling on them. The scaling will also mess with the hardness test because it settles under load, or it will crumble, or make your part tilt a little bit. Also, regarding on tilting, with this table you can only test parallel pieces. You cannot test on a sloped surface. There is a probability to crack or break the diamond, and that's the least thing you want to do. Why don't we just hardness test some things? This is a parallel from a imported parallel set. These served me very well. They are hard, but not crazy hard if I have them right in mind. Keep in mind that the diamond leaves a indentation, so consider if you want a small dent in your part or not. Personally, I don't care too much on my import tooling. So we add the sleeve, preload it back to 0, and drop the diamond. Drop the weight stack that pushes the diamond in. And by the speed this moves, these are not very hard. So we have to wait a few seconds until the needle settles. And then we can lift the weight stack and get our direct reading. And this is surprisingly hard. This parallel is 59 Rockwell C, which is, for a parallel, stinking hard. And before I put it back, I'm going to clean up the indentation from the diamond. Next I have a import 2040-80 block, which is basically a metric 1-2-3 block. Arc Eurotrade in the UK sells these. These have some damaging, so you have to be careful with the stoning. We put the diamond indentation right in the center because we can. Preload it, drop the sleeve, and there we go. This is definitely way softer. This is very soft. So let's get our reading. So this is 25 Rockwell C. So these are basically dead soft. Let's get a file because oh. Oops. Yeah, they are indeed very soft. Okay, so 2040-80 blocks from Arc Eurotrade, very soft. This is a Moore setup block. This should be hard. At least I expect it. And yes, I know that this is awful to watch now because it's a pristine setup block, but this is for the internet. There we go. Let's see if this is also 25 Rockwell C. So we get our loading. We wait a few seconds to have it settle. And let's get a reading. Okay, this is different. This is 63 Rockwell C. That's a significant difference. And yeah, don't scream at me. It's my tooling. And I want to know. This tiny point up here is what the diamond left in the part, so I'm not too crazy about damaging my tool. And I stoned all the material that gets thrown up around the diamond indentation away. This is a Soviet gear cutter, a module cutter. Module 1, number 8 gear cutter. So let's see what our Russian friends did. Let's see. To be honest, I was all day already testing hardness of different things just to learn about the hardness of things. What I can tell you right away, because I tested it, this life is hard. So that's a Soviet gear cutter. I expect it to be fairly hard. And indeed, oh, it's still moving, it's still creeping. So that's 65.5 for the Soviet gear cutter. And somebody told me that these gear cutters I have are one of the lower grades the Soviet industry produced. So, but I know they work. I have both a Chesterman blade, steel rule, Sheffield, England. I think this is supposed to be hardened. And also a blade from a Starrett combination square. This is definitely hardened, as it says on here. So we're going to test both. First, the British one. This is fairly thin. I'm not entirely sure if I get a correct reading on this, but we will see. Well, I can't say if I get a correct reading. I can say if I get a plausible reading. Ooh, this is soft. Oh yeah, this is 44.5 Rockwell C for the British one. Not crazy hard. Also, this is in bananas. A very kind viewer sent me this because I didn't have a scale in banana. So we clean the diamond indentation up and we check the backside if we get a... No, we don't get any push through on the backside from the diamond. So I guess this is still good enough thickness to test the hardness. So let's go for the Starrett. Which is, I hate the scaling. I hate the division lines on the Starrett combination square blade. I hate this. The two double lines in the center is just awful for metric reading. So. Yeah, we're testing without the sleeve. But no, this is not hard. This is 44 Rockwell C. And I will test again just because people will tell me that I'm biased because it's American tooling. I'm not, but I'm not impressed by Starrett tooling at all. Well, the Starrett combination square is a nice tool, but they forgot to deburr it. It's razor sharp, and the steel they use is prone to rusting like nothing else I have in my shop. So yeah, still 44.5. It's both of these scales are about soft. So let's clean this indentation. I expected these to be way harder, to be honest. I expected them to be like 54 Rockwell C. This is like a pre-hardened tool steel Tulox 44. That's the same hardness, and you can file that stuff. I have the inner ring of a shot magneto bearing. This is out of a drill press spindle, but they used to use magneto bearings before angular contact bearings got widespread use. So we drop this in, and let's see how hard this inner race is. Or, in fact, both races should be the same hardness. This should be stinking hard. So we stop here at around 20, and now we get our reading. So we get exactly 63 Rockwell C. Sounds about right. This is a shop-made parallel out of O2 tool steel with a very, very low temper. Means they are like glass. Yeah, this is 65.5 Rockwell C. That's my own parallels. That's a decent hardness. Did you ever wonder how you test your hardness tester for accuracy? Probably not, but I'm glad you asked. You have a box of these, of course. These are hardness testing samples, and they are certified, and they have the actual hardness value etched onto them. This box ranges from 63.4 down to 31.3 on the Rockwell C scale. There is also one Rockwell A, 81.1, but I don't have the testing diamond for this one. So you're not supposed to regrind them if they are used. You're not supposed to use the back side, just front side, and you have to keep a certain distance, a few millimeters between each indentation. Otherwise, the metal that gets moved around by the diamond might interfere with the hardness on the next testing. Work hardening, basically. So you take these and you just take a reading of them. And we make sure they are clean. I know this backside is stoned because I recently used it already. Make sure it seats nicely. Find a nice spot on there. That's a lovely spot here. Get our diamond preloaded. Whoop. Get our sleeve located. Okay, and then we drop the weight stack and get our direct reading. Oh yeah, 60, 61, 62, 63, and some change. So I'm calling this 63.5. And as I said, this plate is 63.4. So yeah, this is a very powerful tool, and with the calibration plates, it's easy to prove it out yourself. If you don't have the sample hardness plates, you are a little bit in a pickle. You can find a friend that has a hardness tester too, and take a high-speed steel blank to him and hope that the steel is good quality and very homogeneous all around. Hardness test it, engrave the hardness you measured at your friend's place with his calibrated hardness tester, and then take a reading with your own uncalibrated hardness tester at home. That would be an alternative. Or you break down and buy the hardness testing blades. They are expensive. One of these costs 300 euros. One of these. They are, by the way, the new and improved triangle format. That's not a joke. That's actually what the paperwork said. I was thinking we could do also a Vickers hardness test because it's a little bit more complicated than just reading off the dial indicator. For that, first we need to exchange the diamond from a conical diamond to a pyramid shaped with a tip angle of 138 degree. So we take the diamond out. And here's the other diamond for Vickers hardness. Goes in. Make sure it's seated up here all the way. And we can just leave away for now. And I was thinking we could use a reference plate from my HRC samples. This is a 61.7 Rockwell C sample plate. And we will use this. We will determine the Vickers hardness and compare it to the Rockwell hardness. So we see if we get a reasonable result that way. Since you're doing Vickers hardness testing, we can select any weight we want. The thinner the material, the less force you want. On very thin pieces, there is a small force range for Vickers hardness that goes up to, I think, 1 Newton, and there is even a micro range for Vickers hardness that is even lower. And you use that to check the hardness on, for example, nitrided parts, case hardened parts, where you do not want to poke through the hardened case. You want to know the hardness of the case or the nitride layer. Let's go for 100 kilograms, which is not entirely true. If I select 100 here, because this machine is basically set up for Rockwell C testing, that's 90 kilograms of testing force plus 10 kilograms of preload. That's what I did with the hand wheel earlier when I moved the indicator 2.5 turns. So this is basically 981 newtons, because 100 kilograms times 9.81 meters second square minus 98 newtons, which is 10 kilograms, is our actual force that we're going to use. I will do that on paper later. It's a little bit confusing, but we're running with 100 kilogram setting here on the machine. We just need to take care of it on when we do the math. And we find a nice clean spot on our sample plate. Crank our table up. First I want to mark an area. I drew a little square so I can identify my indentation later. And we bring the diamond in contact and we release the weight. You don't see much now. The indicator is not moving and we're just waiting about 20 seconds for the diamond to settle. It's like 6 seconds of time with the force applied slowly, and then 20 seconds of waiting until it settles out. Dum, 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 dum. So this is boring as can be, but you get the idea. Let's unload it and get our sample out. There we go. There is our Vickers hardness test of this plate inside this blue square, kind of square. All the other dots are Rockwell C tests. So let's go to the microscope. We're over at the microscope and you're looking through the eyepiece, which I'm not, and here's our test plate, and you can see those circular indentations. Those are from Rockwell C testing. And if we search now, there's our square, and here is our pyramid indentation. And now we measure the diagonal size of this indentation. We orient it correctly. It's a little bit hard to do this through the viewfinder of the DSLR. So we start here, zero out the dial on our toolmaker's microscope, and then we move over, measuring the diagonal of this indentation, like this. This is about right. So this is 0.46 millimeters. 0.46, and we also measure the second dimension from here, because we're building the average of those two measurements. So we start here, 0, and this is 0.44. 0.44. So yeah, that's how you measure the size of the indentation for Vickers hardness testing. Off to the paper. The size of our indentation, let's draw it from a top-down view like this, was 0.44 and 0.46. So the average between those two is, that's D equals 0.45. You calculate that by adding those two up and dividing by 2. Here's the formula for Vickers hardness testing in our trusty Tabellenbuch Metall. And we have Vickers hardness is HV equals 0.1891 multiplied by the force divided by the square of our diagonals. So let's write this down. HV equals 0.1891 multiplied by F D square equals 0.1891 multiplied by, I set the machine to 100 kilograms. 100 kilogram. Multiplied by 9.81 meters per second square equals 981 newtons. That's with the 98 newtons of pre-force minus 98 newtons preload. We don't want that, we didn't do the preloading in this case, so equals 883 newtons. There's a little bit of rounding error in there, but meh. This is good enough. So we have 883 newtons. 883 newtons divided by 0.45 millimeters square equals 0.1891. 1 multiplied by 883 divided by 0.45 square equals 800 and Vickers hardness of 824. So we have a Vickers hardness of 824. So 824 HV, and normally you write the force that you used for your Vickers hardness behind it in kiloponds, not kilogram. Kilopound is 1-to-1 because kilopound is basically kilogram force. But we took away the 10 kiloponds of preload, so it's HV 90. Vickers hardness 90. And this compares, if we take our trusty table here, so we have a Vickers hardness of between 800 and 840, and we have a Rockwell hardness that's associated with it between 64 and 65. So basically 64 and a half. And the test plate, 61.7 HRC. So we are 2.8 HRC off. That's less than 5% off this. Less than 5%. So yeah, this is the Vickers hardness, about the Vickers hardness of this plate compared to the real HRC hardness. So the measured Vickers hardness goes to 64.5 and the real one is 61.7. So we are 2.8 HRC off, points off HRC, and that's less than 5%. So that's the idea behind Vickers hardness. And when we go back here in the book, there's a minimum thickness of the material in relationship to the material, to the force you're using. On HV100, which is a little bit more than we did now, like 10 kilograms or 100 newtons more, the minimum thickness ranges from about 0.8 to 2.5 millimeters. Otherwise, your reading will be off. But you can also go very thin with 0.2 kilograms of force, which my hardness tester cannot do. You can go down to a sample on higher hardnesses down to 25 microns, starting at 100 micron. So pretty universal way of testing. And Vickers hardness is always comparable. You can compare a Vickers hardness that's tested with 90 kiloponds will compare 1-to-1 to one that is done with 0.2 kilograms force. So it's very universal and you can use it for a lot of things. And with the microscope, it's relatively easy to measure these dimensions. So that was a little course into Vickers hardness and Rockwell hardness testing, of course. I hope you enjoyed this. Thank you all for watching, and I'll be back. Long-time viewers of this channel might remember these. These are hardness testing files made by Tsubo-san, the Japanese company. And these are used as an average tool to check hardness. You have the manual up here, and they're quite self-explanatory. They are incremented in 5 HRC, 40, 45, 50, 55, 60, and 65. And you just go through the files against your workpiece or the part you want to check. And once you reach the file that doesn't skid over the surface anymore, you know about the hardness of the part. You have a chart up here. If the HRC 40 file touches the work, your part is about 40 to 42 Rockwell C. If the 60 HRC file hits it, 60 to 62, and so on. It's just easy way to compare. And over here are the hardness Vickers values. And they're to be applied like this on a flat surface, like this, and on a bore with the internal bend of the file. So let's compare this against the Wolpert. I remember these because I cross-checked them with the hardness tester at work to be fairly accurate if used with caution. This is a shop-made parallel out of O2 tool steel, and 40 Rockwell C file doesn't do a scratch. 45 skids right over it. 50, nope. 55, nope. 60, now we're getting into some nope. And we have a 65 HRC file. And this barely scratches it, not really. So we are probably above 65 Rockwell C. Let's go to the hardness tester and check this part. So let's check the parallel. The diamond is exposed, no burrs on the part. And preloaded. Whoop. 150 kilogram, and here we go. So we're here and measure it. 64 Rockwell C. This is this is the upper limit what O2 tool steel can get to. And also that's the upper limit what the hardness testing files can check. So this is a better example than the parallel that we used before, because this is a little bit softer if I remember correctly. So again, we go through the files starting at 40 Rockwell C. This just skids over it. 45 Rockwell C, skids. 50. Skids over it. 55. Nope, nothing. Skids over it. And the 60. Yeah. This wants to bite. It definitely wants to bite into the material, and I'm scratching all my V-block up here. So 60. 65. Yeah, this definitely bites. This definitely takes a cut, a very small cut, because it's between 60 and 65 Rockwell C. Part in, preload it till the needle stops moving, and release the weights. Okay, settles out. Wait a few seconds and see what we get. That's 57 Rockwell C. With the hardness files I got to about 62 Rockwell C. So we are about 5 points, hardness points off, which is still not terrible. Especially considering the price of the hardness testing files, which is about 70 euros. So in case you're curious, this is a very good way to secure a Wolpert hardness tester to a trailer. You bolt it down to a pallet, you bolt the pallet down to the deck of your trailer, you use an additional strap around it, and you strap the whole top of the hardness tester again down to the trailer. And that's a very safe way to transport this thing. Also, you have to immobilize the weight stack and back, for example, by stuffing in some rags. Also, it's a good idea to remove or disengage the linkage on the internals. Unloading is easy with a strap around the neck of the hardness tester, using a ratchet hoist, removing the pallet, and then you can just put it on a small trolley. I have to thank my friend Tom and his father again for horse trading this hardness tester. It's really a nice piece, and it will get use in my shop for sure. And I hope you enjoyed this video about the hardness tester, about the theory behind it, and some construction details of this machine. Thank you all for watching, thanks for the ongoing support, and I'll be back.